For some of the class lecture material, because we're familiar with using the chalkboard, I want to pre-record some lectures using this method. And then we're going to use the lecture time periods for a little bit more discussion and interaction associated with the material. Before we left campus, the last thing that we had talked about was fluorescence, so we pretty much covered that topic. And so we're actually moving into a new topic on atomic spectroscopy. Chapters 8 through 10 in SCOOG talk a lot about this material. So if you need reference in SCOOG, that's where we're going to go. Atomic spectroscopy is essentially the same as UV vis spectroscopy, only we're dealing with atoms rather than molecules. And so there are some differences as a result, but we're still looking at the UV vis region of the electromagnetic spectrum. And so similar to talking about UV vis most recently, this has lots of similarities with us. Atomic spectroscopy is a very old technique. It's associated with emission spectroscopy. I'm sure several of you have seen bright or dark line spectra associated with atoms. And it's been recognized since the early 19th century. Again, the idea of spectroscopy and bright line spectra gave us the indication of quantization or quantized energy associated with atomic energy levels. And so our structure of an atom really came out of the work of emission spectroscopy, indicating that not all energy levels are possible coming after an atom is excited or goes into an excited state. The first analytical application of atomic absorption spectroscopy, so the analytical application of atomic absorption spectroscopy was for the determination of mercury. This was done by Mueller in 1930. So we've been doing some type of atomic absorption spectrometry for almost 100 years. And so first analytical application was in 1930. Modern atomic absorption spectroscopy, so modern AAS is associated with a scientist by the last name of Walsh, and that's in 1955. So although we've been playing with using AAS for determination of metals since the 30s, the modern application is associated with Walsh in 1955. And interestingly enough, there are enough interferences in this that most of the data collected between 1955 and 1970 isn't used. It's considered meaningless because of the interferences. And so most of the accepted data for AAS is greater than 1970. So in terms of quantitation and getting good results from AAS, relatively short period of time ago. And again, the major issues or major problem for this are interferences. And we'll talk about the different types of interferences that are possible in AAS. Since we're starting generally by talking about atomic spectroscopy as a whole, there are three parts to atomic spectroscopy, or three types of atomic spectroscopy that we need to discuss. And in the same way that we've seen for other techniques, such as detectors for FIDs, these all are given acronyms: AAS, AES, and AFS. These are all types of atomic spectroscopy. AAS stands for atomic absorption spectroscopy. AES stands for atomic emission spectroscopy. And AFS stands for atomic fluorescence spectroscopy. Again, these are all types of atomic spectroscopy because we're dealing with atoms. They all involve, at some point, having neutral atoms absorb energy in the UV vis range. Depending on the type of spectroscopy, determines on whether we are dealing with the absorption or the emission or the fluorescence piece, which is also a type of you're looking at the emission from the sample. And so again, these all involve having some kind of metal atom absorb. One of the difficulties is that since this deals with transition metals in particular for quantitation, most transition metals in nature are found in the ionic form, in the form of salts. And so one of the major issues or problems associated with atomic spectroscopy is that atomization process, converting ions to neutral metal atoms in the zero oxidation state. These are going to be gaseous atoms. Again, in nature, we generally find these in aqueous solutions, or we put them into aqueous solutions. But ultimately, to do the spectroscopy on the atoms, we need to undergo this process to get to neutral atoms in the gaseous state. And so, right, similar to what we saw for UV vis, once we get to neutral atoms in the ground state, right, we're then going to deal with some type of light input, right, where that's going to cause an absorption to get to, we'll put this in, right, so this would be our ground state, some sort of light in causing absorbance to get to an excited state, right? And then once we get to an excited state, if we get to light out, right, then we're going to deal with atomic emission and atomic fluorescence spectroscopy. But all of these deal at some point with getting to a neutral metal in the ground state as a gaseous atom so that it can come in contact with light in that UV vis region, absorb, get to an excited state. Once we're in that excited state, then we can potentially get to emission or fluorescence. And we'll talk about the major differences between emission and fluorescence in just a little bit. Atomic fluorescence, right? We excite atoms using light, right? So this process, right, of taking this atom to the excited state using light is particular for fluorescence, right? The difference between that and emission, you're still using or getting to an atom in the excited state, is we excite atoms thermally. So one of the things to keep in mind is that fluorescence is much more selective in that only those atoms that absorb specific wavelengths of light are going to make it to the excited state. Whereas for emission spectroscopy, anything, if I put in enough thermal energy, anything could be excited to an excited state. And so emission spectroscopy tends to be a little less selective as a result. There's various ways that we can excite atoms thermally for atomic emission spectroscopy. The three most common ways to excite atoms thermally are using an arc, using a flame, or everybody's favorite, using a plasma, right? So these are all ways that atomic emission spectroscopy will get atoms from the ground state to the excited state. Fluorescence will use light to excite atoms. as a result. So there are differences between those two. Atomic absorption spectroscopy is similar, right, to UV vis in that it's an absorption technique, but it's specific to atoms. The major difference associated with atomic absorption spectroscopy, right? Major differences between this and UV vis, right, have to deal with the light source, right? And the second part has to do with the cell. I know not everyone was able to see the demonstration of the AAS in use. I'll try to also get a YouTube video of that posted, and I'm going to collect data for you guys. But the two major differences, right, even though we're still working in the UV vis region, is for AAS, we have to use different light source, and we have to use a different cell. We can't just use a quartz cell, mostly because of this process of atomization that needs to occur. And so most commonly, what's used as a light source, again, another abbreviation, is called a hollow cathode lamp. We'll talk about those in a bit. And the most commonly used way to get atoms from a neutral ground to a neutral ground state, that atomization process, is we often use a flame. There are some other options, and we'll talk about those a little bit later, but these are the major differences for UV vis compared to AAS, because we're dealing with atoms rather than molecules as a result. So for each of these things, emission, fluorescence, we can think about what the instrument diagrams, right? What the instrument diagrams are going to look like for each of these things. And again, based on what we're trying to measure, the instrument design is going to look a little bit different as a result, right? So for example, AAS is going to look a lot like UV vis, right? I need some sort of light source. As I said, for the most part, this is going to be a hollow cathode lamp, right? That then is going to go through my cell. So this is my source. This is my cell, right, which is going to be a flame, and we used an acetylene air flame when I demonstrated for that for you. That then has to go through a wavelength selector, monochromator, right? And once we go through our monochromator, that's got to go into some sort of signal processor. And then a detector. Right? Very similar to UV vis. Major differences are going to be your source and your cell. Monochromator usually comes after the cell rather than before it, because our light source is going to be a line source, unlike a continuous source like we used for UV vis. So this would be the basic layout or design for atomic absorption, right? Atomic emission, since we don't use a light source, since we don't excite the atoms with a light source, we excite the atoms in the flame, right? We are going to use a flame followed by a monochromator. We'll put this down here. So for AES, we don't need a lamp. We're looking at the light emitted after the atoms are excited. And we're going to do that thermally in our flame. So this is going to serve for atomic emission spectroscopy as both for atomization, getting the atoms, the ions into the neutral atom, and for excitation. And again, we could use a plasma or a higher temperature flame to help with that. That then, right, is going to go through our monochromator, right, to make sure we're just looking at that one specific wavelength. And then that's going to go to your signal processor and your detector, which are kind of connected, and then your readout, right? And we'll talk a little bit about the signal processors for this. An instrument diagram for fluorescence, right, is going to have the lamp, because that's what we're going to use for excitation. So we're still going to use a lamp for fluorescence. That then is going to go through a flame, right, where I get atomization to occur. And now we don't want the detector to be in line, very similar to fluorescence for molecular spectroscopy. In fact, it's going to be at a right angle because we just want to see the light emitted, right? This then is going to go to a monochromator so that we can get the emitted light, not the light from the lamp. We don't want to look at absorbance. And then that's going to go to your signal processor and detector, or vice versa. As I said, these are kind of combined detector signal processor as a result.